Very good morning, students. Hope all are safe and healthy. And in today's class, this is the last topic of your module 4. So, here you will be learning about the stable operation of the IC555 timer. So, it is the most common application of the IC555 timer, and it is also known as a stable multivibrator or a clock circuit. So here the construction of this stable multivibrator is we are using the IC555 timer along with two external resistances RA and RB and capacitor C, and these three are connected in series, and it is connected directly to the DC of the power supply, and this will set the timing of the intervals of the output, and rest it is the pin configuration of your IC555 timer, and as usual pin 1 is grounded and 2 and 6 which are the inputs for the comparator, it is short, and it is connected across the capacitor C. So whatever the output voltage across the capacitor will be taken as an input for the pins 2 and 6. And coming to pin 3, it is the output pin of the 555 timer, and 4 it is the reset pin, and 5 it is the control input, and usually the control input will be fixed and it will be equal to 2 by 3 times of VCC. So usually this control input will be connected to the ground across a capacitor of value 0.01 microfarad, and pin 7 is the uh, discharge pin, and this pin is taken from the output of the discharge transistor, and this is connected directly to the RB, and this discharge pin helps the transistor to discharge across the resistance RB when the transistor is in on, or whenever the transistor is in off, the capacitor will start charging via RA and RB. And 8 as usual, it is the voltage DC voltage input, which is plus VCC, and as you know this DC input voltage should be between 5 volt to plus 5 volt to plus 18 volt. So coming to the operation of the stable multivibrator, as soon as the DC voltage VCC is connected, the capacitor start charging through the resistances RA and RB. So when the voltage of this threshold pin tends to increase beyond 2 by 3 VCC, the first comparator will be saturated, and this will trigger the flip-flop. That is the output of the comparator 1, it is connected to the reset of the flip-flop. Hence the reset will be 1. If reset is 1 for the SR flip-flop, the output will be reset, that is Q will be 0 and Q bar will be 1. As Q bar is connected to the inverter to get the output of the 555 timer, the output at pin number 3 is low, that is the output of the 555 timer will be at low. At the same time, the transistor which is connected to the input of the transistor is connected to the Q bar of the flip-flop. So this transistor becomes on, and this will cause the output at pin number 7 to discharge the capacitor through R2 with a time constant of RB into C. As the capacitor starts discharging, if it falls below 1 by 3 times of VCC, the second comparator output will cause the flip-flop to reset. That is the reset will be 1, and output will be low, and the Q bar will be 1. Again the transistor goes to off state. If the transistor is in off state, the output at pin number 7 discharge will make the capacitor to start charging again through RA and RB with a time constant of RA plus RB into C, and the time constant is represented by tau 1. So this cycle again repeats continuously, and if you see the waveform of the 555 timer and the capacitor charging and discharging, you can understand better. So when the capacitor start charging, the output of the 555 timer will be high. When it is discharging, it will be low. So by changing the values of R1, RA, RB and C, we'll be able to change the timing of this output waveform, that is either T high and low can be varied. And the capacitor periodically charges and discharges between 1 by 3 VCC to 2 by 3 VCC, and this length of the time that the output remains high is the time for the capacitor to change from 1 by 3 VCC to 2 by 3 VCC. And we can calculate this voltage as follows. As you know, the voltage across the capacitor, it is calculated using this equation. VC is equal to VCC into 1 minus e power of minus t divided by RC. Let us assume T1 is the time taken by the capacitor to charge from 0 volt to 2 by 3 times of VCC. Then VC can be equated to 2 by 3 VCC, and solving this equation you will be getting T1 is equal to 1.09 RC. And let us again we will assume T2 will be the time taken to charge from 0 to 1 by 3 VCC. So equate this VC to 1 by 3 VCC and calculate what is T2. So we are getting the equation for T2 as 0.405 R into C. So the time taken to charge from 1 by 3 VCC to 2 by 3 VCC, that is nothing but the on period time. So it is taken as T high. So the difference between T1 and T2 is found. It is equal to 0.69 R into C. Whereas for the circuit what we are analyzing, the resistance is sum of RA and RB. So replace this R with RA plus RB. T high can be written as 0.69 into RA plus RB into C. So the capacitor discharges from 2 by 3 VCC to 1 by 3 VCC, and the voltage across the capacitor can be taken as 1 by 3 VCC to 2 by 3 VCC into e power of minus t by RC. And even we need to calculate the discharging period also. So by equating to 1 by 3 VCC, we can calculate what is T low. So we are getting T low as 0.69 R into C. Since the capacitor discharges across via the resistance RB, T low can be written as 0.69 into RB into C. So the total time taken for completing one cycle, it is T is equal to T high plus T low. By adding these two, we will be getting T as 0.69 of RA plus 2 times of RB into C. And as well you can calculate the frequency of oscillation as F is equal to inverse of T. So take the inverse of this, and we are getting finally the frequency of oscillation as F is equal to 1.45 divided by RA plus 2 times of RB into C. And also we can calculate the duty cycle of the stable multivibrator. And duty cycle, it is nothing but the ratio of the on time to the total time for one cycle. So the on time period is due to the resistances RA and RB, that is the charging time, it is via RA and RB. So the percentage in duty cycle, it is written as RA plus RB divided by the total time taken by the capacitor for both charging and discharging. Just now we have calculated, it is RA plus 2 times of RB. In terms of percentage, you can write it as percentage D is equal to RA plus RB divided by RA plus 2 RB into 100. And also you can, if you want the on time and off time period to be same, we can change the values of RA and RB. Will design such that we are getting 50% duty cycle. That is, you need to equate this to 50%, and any one value, either RA or RB, you assume and calculate the other one, so that you'll be getting equal T on and T off period. Thereby you'll be able to generate a square wave. And whatever the percentage it is given, if it is 70% means equate to 70%, assume any either RA or RB, and design the circuit based on the values of RA and RB. You can implement it for any percentage of duty cycle given. And we are at the end of this module 4. This completes your module 4. Keep watching all the videos, right? And prepare well for your internal exam. Give your best, and keep texting me whenever you have any doubts. Okay, thanks for watching. Let us continue in the next video. Thank you.